Konnichiwa. O genki desu ka? Yarimashou. Welcome back, y'all. We are starting our study of the single pendulum problem. Before we do any work trying to state equations to describe the motion of the pendulum, the first thing that we're going to do is just get acquainted with how single pendulums move. With that in mind, let's define what the heck a single pendulum is, and let's visualize that using an ideal model. Specifically, we're going to construct something called a simple gravity pendulum, which is an ideal mathematical model of a real pendulum in life. To get started, let's take a look at what a pendulum looks like. This is a real pendulum, not ideal for sure. This thing has a cord that attaches to some fixed structure, in this case my hand that's not moving, and then it has a weight at the bottom, and then it swings back and forth. When we create the simple gravity pendulum, what we're going to do is idealize each of those components. So here's a diagram of a simple gravity pendulum. When we're looking at that mathematical simplification or idealization, we're going to name three distinct components. First, we're going to talk about something called a bob. In normal words, that would be like a weight that is the end of one part of our cord. The other part is, of course, our massless, inextensible cord that does not change length. One of the reasons that I said that this was not ideal is this is definitely not inextensible. I mean, that is extendable and unextendable, compressible. In the ideal version, we're assuming this thing is like a straight line with constant length no matter what. The third thing that we need is a fixed structure to which we're going to attach the other end of our cord, and that thing doesn't move. With those three components, the bob, the cord, and the structure, we have a simple gravity pendulum, a model of a real pendulum in life. The next thing we're going to do is actually discuss how to attach those three components together to allow the pendulum to move as we expect. The first thing we're going to do is take our massless, inextensible cord, the cord that doesn't change length and has no mass, and we're going to attach the fixed end of that cord to a frictionless pivot point on our support structure. That pivot point allows the cord to move back and forth, to pivot side to side. Frictionless means there's no energy loss there. This is not like a swing that you get onto in a park. You ever swing on the park, you do two or three kicks, and then you hear the thing go, and you go to a stop because there's friction in that. This pivot is not like that. It will go back and forth forever without losing any energy. And then the connection at which the cord meets the stable support structure is called the fixed end of the cord because it's fixed in one position, even though it moves back and forth at that fixed point. Very similar to a swing. The other thing we're going to do is we're going to connect the bob or the weight to the free end of the cord. The free end is the one that is not fixed. It's the one that is free to move side to side. When we do this, we hang the free end from the pivot in a downward position so that it is free to move side to side. And then we say that the cord is inextensible, meaning that along this motion, there is no change in length. There will always be a constant distance between the pivot and the bob at the other end. In my real pendulum, that would look something like this rather than something like this, right? That is not inextensible. I have to have that length non-changing. That's the assumption that the cord is a constant length. With those three components attached as we described, we can give the bob an initial displacement so that it will swing back and forth. What I mean by this is if I let it come to rest, it's going to come to an equilibrium position and it won't move for the rest of time. But if I displace that bob, all of a sudden that pendulum has motion. Another assumption that we make in our simple gravity pendulum, the ideal mathematical model of a much more complex real-world scenario, is that when we displace that bob, we have set up the structure and the displacement in such a way that the bob traces out a path only in two dimensions, in a plane. So what I mean by that is, in this situation, if I displace this thing this way, that is pretty much in a plane. However, there are situations in real life where it could not be in a plane. You see how that's three-dimensional motion? I go up, down, side to side. That's not what's happening in a simple pendulum. In a simple pendulum, that bob is stuck in one dimension along the x-axis and one dimension along the z-axis. There is no back and forth motion to and fro away from that plane. Under that assumption, it is quite natural to see that because the chord is constant length and we're moving back and forth along that pivot, that path that the bob traces is actually going to be an arc, like a part of a circle. In fact, if I took the bob all the way around, this thing would inscribe a circle in the air whose radius is equal to the chord length. That's not what we're doing in a simple pendulum, at least for small angle approximations. We're going to let that chord move back and forth for a small number of angles, and that arc is the path that it traces out, that the bob traces in that two-dimensional plane. The last thing that's worth noting is that this whole time we've assumed that we're on the surface of a planet that has gravity. Let me describe that in a different way. When I set up this pendulum and I hang it from the position, there's going to be a force acting downward that pulls that bob towards the ground. If we set it up in such a way that the chord is lined up vertically so that this bob creates a 90-degree angle, it's a perpendicular to the ground below it, we're going to call that position of rest. Do you see how that thing comes in a position of rest? That position is going to be called equilibrium position. A more formal definition for this particular scenario is that when we have the bob start at rest and the chord hangs at a 90-degree angle from the pivot. So when we're looking at that 90-degree angle where the bob is at rest, the point at which that thing comes to rest, the minimum potential energy of that system, we're going to call the equilibrium position of the pendulum. And what I mean by minimum potential energy, when that mass is down towards the ruler, the height of the mass away from the ground below it is the smallest. Physicists say that that is the minimum potential energy. That is one way we're going to categorize the equilibrium position of this system. Notice that under this definition of equilibrium, the chord at that position is completely vertical, doesn't tilt one way or the other, and it forms a 90-degree angle with the ground below it. We've gotten more and more sophisticated as our model is being built. We have three components: a bob, a chord, and a structure. We have a pivot point that allows motion. We have two-dimensional travel, so only in the X direction and the Z direction. It's allowed to go up and down, and it's allowed to go side to side. We've given a name for something called the equilibrium position, where it comes to rest with minimum energy. The last two assumptions we're going to make about this ideal model have to do with physical properties of the surrounding environment. Specifically, we say that the motion of the mass does not lose energy due to friction or air resistance. In other words, this bob, if I set it into motion, if I displace it, will go on forever. It will never stop going. There's no wind or air resistance, and similarly, there's no friction or energy loss having to do with the connection to the structure. This is literally an ideal pendulum. The second assumption is a gift to physicists, which is that as the pendulum bob moves from side to side, there's no experienced change in the gravitational potential. So there's not like less gravitational force on one side and more gravitational force on the other side. If you had a pendulum that was like hundreds of thousands of miles long and you started it at one side of the Earth and then let it kind of go through the atmosphere and come to the other side, that gravitational potential assumption might go away. But on the surface of the Earth, in the coordinate system that we're going to study this, and in local space, we're fine on that, right? This is where I want to use our imagination a little bit. Pretend I have a laser light, which you see here, and I can shine a light vertically down onto the bob, directly onto the ruler, and that light always stays 90 degrees. So as I move that bob back and forth, that light actually stays right above the bob and it tracks onto the ruler. If we were able to shine such a light overhead of the bob and project the shadow down onto the ruler, we could call that shadow the orthogonal projection of the bob onto the measurement system. Another way to say that is if you drew a line from that shadow up to the light, that line would always be 90 degrees from the ruler. Not only that, but we could actually track these different positions along the ruler using variables. So if we projected a light directly above the equilibrium position, let's call that position x1. the position of the equilibrium place that the bob rests along the ruler. And then when we project the bob down orthogonally onto its shadow, let's call that x1 of t, which is a function. The reason that it's a function is as that bob moves in time, that orthogonal projection, that shadow, is going to move along that horizontal axis back and forth, and the position is going to be a function of time. What's really nice about this projection construction, about moving the pendulum out of the air and onto the ruler, is that we can study the motion of the pendulum using the proxy measurement of position of our shadow. Later, we're going to call this linearization because I turn nonlinear motion, I turn motion along the edge of a circle into linear motion, which is motion along a line. We're going to see that there are some assumptions that we need to make in order to have that linearization be valid, and specifically the angle theta between the vertical equilibrium position and the position of the rod at time t. That angle has to be limited in order for this projection to work out well. We're going to call that the small angle approximation. Don't worry about that. It just means we're not swinging our pendulum wildly from back to front. We're literally just going to and fro in this direction. With that in mind, let's make the assumption that we do this small angle, that we perturb the mass just a little bit, and then we watch it move back and forth, studying the motion of the shadow under the pendulum and trying to get a sense of how this thing is behaving. A great place to start is by slowing things down and looking at the ideal case. What you see on screen here is actually a visual representation of the dynamics of our simple gravity pendulum. What I want to do is play a animation that gives us a sense of what's happening here. So before we do that, let me name the features that you're looking at. Here we have our massless inextensible chord. At the bottom we have this bob. We're going to displace that bob from our vertical equilibrium position. I've marked equilibrium in yellow like we did in our notes. When I displace my bob to the right, I'm going to do it so that it reaches the maximum right position, or what I might call the forward extreme position. That I'm going to mark by purple, and when I project down onto the ruler, the purple dot represents the farthest motion to the right that my bob will travel. As I move down along my path, my arc path that's part of a circle, whose length is determined by the length of the chord, I'm going to move through equilibrium position in yellow, all the way over to the left extreme point, or the most left position of that bob. When I project down onto my ruler, that projection point is seen in pink. So the right projection is in purple, the left projection is in pink, and then the equilibrium is in yellow. And that pendulum is going to move from left to right to left to right. Moreover, I can actually track the position of my shadow under the bob, and I can compare that position to the equilibrium position. So at the start of things, that distance between the shadow under the bob and equilibrium is going to be maximum. That's going to have maximum displacement. As I move towards equilibrium, my displacement is going to decrease, and I'm going to highlight the 4 phases of this motion using 4 distinct colors. Check this out. I'm going to use the first phase, which is the first fourth swing. I go 1, 2, 3, 4. We call the entire motion one period of motion. These individual swings we're going to call a fourth of a period, and we're going to color code the position of the shadow along the ruler based on which fourth period swing the pendulum is in. Moreover, on the right hand side, not only are we going to visualize the displacement, the distance between equilibrium and the shadow based on the frame of reference we've imposed. So in this case, we say that positive direction moves to the right, negative direction moves to the left. So when I start my motion, I must have positive displacement. As I go through equilibrium position, notice I went to the left, that's negative displacement. I continue going negative until I get to that left extreme point, in which case I turn around. So I'm going negative, negative, negative. I turn around and then I go positive, positive, positive. I'm going to the right until I get to the equilibrium position. At the equilibrium position, I have zero displacement because I'm where I started, so to speak. And I continue to swing all the way to the right extreme point. Now, you fans of calculus will like this. Not only can I measure the displacement, the change in position, the length between equilibrium and the projection, but I can also measure the speed at which that length changes. In other words, I can graph the velocity, that's that bottom graph that we see here, and notice that my velocity is maximum in the negative direction. It's a negative velocity because I'm going to the left when I'm at equilibrium. As I move past in equilibrium and I go all the way to the left extreme point, my displacement is minimum, meaning I moved as far left as I can, and my velocity is zero. And what that says is at the top of a swing, we actually are not moving for one moment. If you're on a swing and you go up to that top, there's a point at that really, really apex that we stop moving completely. That's exactly what we see here. Then I'm going to move in the positive displacement regime, which is to the right. And I notice when I get to equilibrium, my velocity is maximum. In other words, at the bottom of my swinging motion, I'm going as fast as I can in the entire process. And you've probably felt this if you've ever been on the swing. The fastest that you go is at the bottom of your swing. The slowest that you go is at the top of your swing. With that in mind, let's watch one full period of motion just to see what this looks like in super slow motion. I will narrate this in order to call attention to salient features of the graph so that we can refer back to those later. Let's begin. We start on the rightmost displacement. So I take my mass, I bring it all the way to the right as much as I can. At this point, the mass is moving back to the left because gravity is actually pulling that thing down. The rod is inextensible, so the downward motion actually gets translated into left motion. As I do that, the difference between my shadow projection and my equilibrium decreases. In other words, my displacement is going down towards zero. That correlates with my velocity, the speed of this thing, increasing in the negative direction. So I'm going down and I'm getting bigger and bigger and bigger. As I move through equilibrium position, I start to slow down because now on the left-hand side, gravity is pulling this down. That rod is inextensible, which means that I'm now kind of being pulled back towards equilibrium. As I do that, I get farther and farther and farther and farther left until I've maximized my left position. I'm in the left extreme position. The moment that I meet that left extreme position, I actually have zero velocity, meaning there's a point at which I stop moving. After I stop moving, I switch positions back towards the positive. In other words, I go from negative motion to positive motion, and I start traveling towards equilibrium again. My velocity is positive because I'm moving to the right on this 3/4 period. So all of the caret orange, yes, that is actually caret orange. All of that 3/4 period, I am moving in the positive displacement regime, but I'm still left of equilibrium, which means I'm below the axis. Then I go to the last fourth period, the last fourth swing. And this point, I am moving in the positive direction. I'm above the axis, but I'm doing so at a slowing rate. My velocity is maximum at the bottom, and then it gets smaller and smaller and smaller, which we see here. My velocity is decreasing until I get to the right extreme position, which is that upper position. and then my velocity will be 0, and my displacement will be maximum in the positive. Now notice we didn't actually track the exact position of the bob on the chord. What we tracked was the projection of that bob, the displacement of the shadow along the ruler. The second thing that I want to notice here is, do you remember what the derivative of cosine was? Check this out. Here, this is a cosine curve because I start on the right side and then I move in time. That gets a cosine projection, and the derivative of cosine is negative sine. That's exactly what we see here. If I want to know my displacement, I look at the cosine. If I want to know the change in that, I look at negative sine. All of this helps us get our head around how we can use the math we've studied to discuss getting onto a swing at a local park, or another way to say that, to discuss the natural frequency of a pendulum. And what I mean by natural frequency is, if we don't connect the pendulum to anything else, what is the tendency for that motion? What is natural for that pendulum to do? And we see that the natural motion looks like a cosine. In the next video, what we're going to do is start to analyze the forces on this. And what I want to say is, notice that we only have in this system the initial displacement and then gravity. And gravity, what we're going to do is see that gravity can be decomposed into a downward force, but that force translates as a component in the direction of the chord and a component towards equilibrium. So here, as gravity acts on this system, I get down in equilibrium. In this case, gravity is directly orthogonal, it points downward, so there's no left or right force. And then the thing was already moving, so it actually moves up this way. Gravity is continuing downward, and I get this kind of horizontal component of that force of gravity moving me back towards equilibrium. We will use that analysis to form a differential equation that governs this system. The point of this analysis is just to get our head around, what do pendulums look like by slowing them down. With that, we are now in position to do the next phase of our study, which is to come up with a differential equation that describes this motion. That's exactly what we'll do in the next video. See you there.